Hello everyone, I am Vivian Gomez, an instructor professor at the University of Los Andes in Colombia. Today I'm going to talk about my research with Pablo Figueroa and Aldo Lowe, titled OPVSim, applying a graph-based methodology for VR training in guided learning of emergency procedures in a ship's engineering room. This research stems from the fact that in numerous contexts, such as industrial skills training like manufacturing, maintenance, assembly, and military environments like navigation or aviation, it is crucial to train personnel in decision making and the use of a specific machinery, such as control panels. In particular, because currently in such contexts, many procedures are trained in closed experiences that do not allow for human errors or interaction with real subjects or machinery. Our goal is to address this gap by using a VR simulator for training and guide procedural learning. That is, learning sequences of steps or instructional activities that require students to perform specific tasks. However, to create such systems, it is important to apply existing guidelines and methods to ensure their effectiveness. As authors have mentioned, little is known about creation methods, and there is a fragmented space for creators in terms of technologies and a lack of guidelines. Therefore, we aim to create our VR simulator using an existing methodology in the literature called Protocol VR, which is an iterative process for designing and implementing VR simulators for training in multidisciplinary teams. This aims to report the use of the methodology and detail its applied steps in a specific real world context, as we believe it will help bridge this gap and support the definition of guidelines and standards for the creation of VR training simulators. In this way, our research has three main contributions. First, the design and implementation details explaining how Protocol VR methodology was applied and adapted to develop our VR simulator. Second, the VR trainer evaluation for a fuel leak scenario involved 16 cadets and 16 officers. And third, the lessons learned during their design and development of the VR simulator for a project with features that are generalizable to procedural training simulators. To that purposes, we present OPVSim, a simulator created using Protocol VR methodology. It is a VR training simulation for guided procedural training on emergency scenarios within an engineering room on a ship. To apply this methodology, OPVSim incorporates key characteristics essential for any VR training simulation. The project involves a specific audience, which in our case consists of trainee cadets and experienced naval officers who manage and make decisions in the engineering room during the emergencies. The project involved a multidisciplinary team consisting of two developers, six naval officers, and three designers. The institutions involved in the development of the simulator were located in different cities. Therefore, requirements had to be gathered remotely, including defining the simulation steps and specifying the virtual environment. The simulator environment would result in virtualizing the engineering room of a naval vessel in our fleet. The VR simulator aimed to provide guide training for three cases of emergency, which involve steps for managing a control panel and decision making with the crew. During the creation process, following the methodology guidelines, prototypes of varying fidelities were developed for the virtual environment to facilitate discussions with stakeholders. These include metaverses built using 360 degrees images, environments with gray vaccine, and 3D color mockups, achieving the final environment. Additionally, the simulation scenarios for each emergency case to be trained were constructed in the form of graphs to allow learners to have multiple paths and steps to reach the same goal. The graphs allowed each scenario to be modeled with the help of experts, initially using natural language description of each step during the design phase, and then translating them into functions to define user actions and simulator responses. Additionally, since the focus was on guide learning, supported elements and immediate feedback were provided at each step, like highlighting our areas, using our rows to point our interactive objects, lever movement marks, human guide giving instructions, feedback on decision making in orders or dialogues with staffs, and open dialogue window for giving orders. To optimize development time, the graphs were imported into Unity to manage the simulation. In this way, traversing the graph allowed for managing the simulation, executing nodes, and moving the path depending on the user interaction and system decisions. In this example, one of the graph nodes is shown, which allows for executing the expected simulator actions at that step. For example, here we can see that this officer follows the simulator actions. First, look at the player. Second, go to the closet. And third, activate an animation. In this example, an expected user action is shown, phone call bridge, which means that the system waits for this event, the user needs to call the bridge, before executing the simulator actions. To evaluate the effectiveness of the final prototype, we assessed it with a total of 32 participants, divided into groups of 16, experienced officers, group 1, and training cadets, group 2. We administered pre and post simulator questionnaires to evaluate its impact. Participants used the simulator for 20 minutes, being trained on only one emergency case, full leak. To achieve this, training performance was assessed using 6 questionnaires: participant demographics, pre-training knowledge, presence questionnaire, workload questionnaire, post-training knowledge, and usability questionnaire. According to Shapiro task and QQ plots, technology score metrics follow a normal distribution in both pre and post test. Descriptive statistics also show an average improvement of 1.42 in the overall group. It is important to highlight that Group 2 show a greater improvement, with an increase of 2.62 points and a higher post score of 4.25 compared to experienced officers in Group 1. The results of a priority test indicate that the difference between pre-test and post-test scores is statistically significant for both Group 2 and the complete group. This demonstrates the effectiveness of our simulator for guide procedural learning in CAT training. The perceived workload was low to moderate. Mental demand was the highest, reflecting the cognitive challenges of the learning task. Results showed high usability with a score of 46.9 and a strong reliability according to Chromebrush Alpha. In terms of lessons learned, when using metaverse and graph tools, it is important to consider the technical learning curve. Prior training is essential for experts to effectively use these tools, particularly for capturing special requirements and using Twine. To facilitate tool integration, we found that written manuals and joint editing sessions played a critical role in ensuring success. Furthermore, collaborative sessions are crucial when defining error cases and feedback notes, as experts should avoid omitting what may seem like obvious cases. For example, in one instance, an expert described a step as the engine must be disengaged, but the action actually involved at least 6 additional steps. This study had several limitations. First, the small sample size may affect the robustness of the results. Second, participants had varied levels of experience in VR, which influenced their interaction with the system. And lastly, we didn't compare with other learning methods, such as a control group, due to the logistical challenges in our Navy. In conclusion, this case study demonstrates the successful design and implementation of VR simulator for guided learning using Protocol VR. Evaluated with 32 Navy officers, the simulator showed significant improvements in procedural knowledge, usability, presence, and workload. The results indicate that cadets effectively acquire procedural knowledge, highlighting the potential of VR to enhance specialized training and improve practical skills in complex technical tasks and machinery interactions. Thank you for your attention, and if you have any questions, feel free to contact us.